Okay. Good morning. Few announcements actually. So first, well, the deadline for the quiz and lab 3, both of the deadlines are today. Don't forget that lab's deadline is 4:30 and then quiz deadline is 11:30. I will announce today that I have decided to what's the good term for that? There won't be lab 5. So there would be only one more lab, and that would be lab 4. So what's going to happen is the deadline for lab 4, which is your final lab, will be the deadline that was announced for lab 5, which means that you will have 4 weeks, almost 4 weeks to do lab 4. In terms of workload, lab 4 is very similar to lab 2. So I think the best way to approach it is to shoot for its original deadline and then go from there instead of waiting for the deadline, the actual deadline to come. With regard to machines, I think we're gonna install 15 more machines for the final lab. So hopefully we don't get to the messy situation we had with this lab. In terms of kicking each other off, I just talked to the staff. So if I'm not mistaken, right now, CPU 1 to CPU 5, you can kick off people from, but then the rest of the machines, you cannot kick anybody off of them. So it was changed like a few minutes ago when I talked to the staff. So yeah, anyways, that's another story. What else? Yeah, so I will talk about lab 4 during the tutorial today. So that's pretty much it. Now, we are really behind last term in terms of lectures. I don't know how that happened, but it happened. So let's get into the lectures. Okay. Yeah, we were talking about scheduling a mixture of aperiodic and periodic tasks. We talked about 2 extreme cases. One was giving aperiodic tasks the highest priority, so whenever they come in the system, they get served. And the other extreme is to give them the lowest priority, meaning that if you don't have any real-time, any periodic tasks, then run them. That's basically what you're going to do for lab 4, actually. So we're going to go with that extreme when it comes to normal aperiodic tasks. Then we said, okay, there is also a middle ground, and that would be periodic servers. The idea behind periodic servers is that they're going to be like some notion of, you know, some representative of aperiodic tasks. So we're going to give the periodic server a period and a budget. Now, depending on what kind of scheduling policy you use, how you refill budgets, you would have different methods. We talked about polling server, which used rate monotonic, and the polling server would terminate if its queue was empty. Then we talked about another another periodic server called deferrable server. So with that, you still use rate monotonic, but with that you don't terminate if you don't have a job in your queue, if you don't have any aperiodic task in your queue. Instead, you block, and if you get a task later on, you unblock, and if you have a chance, you can run that task. The last one, which I couldn't finish last lecture, was the total bandwidth server. So the idea with this is to, instead of using rate monotonic, use EDF. Now, with this, we're going to set a threshold utilization for aperiodic task. Usually the way that this threshold is set is we look at our periodic tasks, see how much they utilize the server, right? Utilize the CPU. Let's say if they utilize the CPU by 65%, then we have 35% extra that we can use for aperiodic tasks. So that we set that threshold UTBS to 35. So this is a threshold that we set, and the meaning of it is that we want. So right now, the purpose of this TBS server is to assign synthetic deadline to tasks. And by setting synthetic deadlines, we're going to create synthetic utilization. We want the sum of this artificial utilizations to be less than UTBS. And if that's met, if we can do that, then, well, our system is less than 100% utilized, so EDF can schedule all the tasks. How do we achieve that? Well, here is how we can set the deadline for aperiodic, for the ith aperiodic task. So DI becomes the max of the deadline for the previous one and the arrival of this task, this aperiodic task. So whichever is the later. So if some task arrives before the deadline of the previous one, this becomes the deadline of the previous one. If a new task comes after the deadline of the previous one, then we pick its arrival, plus CI, which is the execution time of task I, divided by this threshold. Now, if you do the math, you will see that no matter how many aperiodic tasks you get, sum of their utilization is always less than UTBS. And it's easy to check. So here is an example. Let's say we have a system with two periodic tasks, T1 and T2, 3.1 and 6.2. So we see how much they're utilizing the CPU. Well, it's the utilization that they're imposing on the system is basically 1 divided by 3 and 2 divided by 6, which is basically 2/3. So 2/3 is going to go to the periodic tasks. We have another extra 1/3 that we can use. So this 1/3 becomes our UTBS. Here I'm running an example with those two tasks and setting UTBS to this 1/3. As you can see, I have marked the arrival of T1 and T2. Let's say I start with no aperiodic task in my system. Well, the deadline of T1 is earlier, so T1 gets the CPU. Let's say at this point, at time 1, an aperiodic task comes that has an execution time of 1. So note that here I'm assuming that I know the execution times of tasks that are arriving. And if I don't, then this TBS cannot work, right? It's assuming that you know the execution time of your tasks. And that's an assumption that we made, actually, if you remember, even with EDF, when we're checking the schedulability, we have to somehow come up with the utilization, and for the utilization, we used the execution time divided by the deadline. So we're kind of assuming that we know, and that's an assumption that is not that far away from reality in real-time systems. Real-time and embedded systems, you really want predictability. You want your tasks to behave predictable in a predictable way. So it's a usual assumption that people make in real-time systems, that they sort of know at least worst case execution time of their tasks. Okay, so with all of that, let's say this is what we have. We go to this formula. So there is no previous task to consider. So this max becomes AI, which is A1, and that is 1. So we set the deadline to be 1 plus. Now CI is 1, UTI is 1/3. So 1 plus 1 divided by 1/3, and that would be 4. So we set this is the synthetic deadline and artificial deadline for this aperiodic task. We set its deadline to be here. Now, okay, so I have two jobs now in my system. This is an aperiodic job or task, and this is a periodic job I have. I look at their deadlines. This aperiodic one has a lower deadline, earlier deadline. So this guy gets higher priority. It runs. Now this one runs, and let's say at this point I get a new arrival for another aperiodic task. What do? Well, I again go to the formula. Now I'm gonna do max of the deadline, the arrival is 3, and the deadline for the previous task is 4. So max of 3 and 4, which is 4, plus, now this guy has an execution time of half divided by 1/3. That would give me 5.5. So I set the deadline to be here. Okay, what do I have now? So at this point in time, I have one job from T1 and one job here, this new arrival. Which one runs? The one that has a earlier deadline. So I run the one that has the earliest deadline. And then oh, sorry, this guy also existed. I forgot. This guy needs 2 time slots. So we still have this as well. But then this new arrival has a earlier deadline than both of them. So this is how it's going to work. At this time, we basically can choose any of these two, right? It doesn't matter. Both of them have the same deadline. Either choose this one or this one. It doesn't really matter. And so on and so forth. So you can run this example at home. I actually have different, arrivals, and then I calculate their deadline, and then you can see that the schedule is basically earliest deadline first. And as long as you follow this formula, your system is always schedulable. One thing that could happen is you could start accumulating aperiodic tasks in your queue, right? So if you get a lot of aperiodic tasks more frequently than what you're able to execute them, then the queue for aperiodic tasks is just exponential, not exponential, like I think it exponentially goes up. But anyways, so this works from the perspective of the scheduler. As long as you follow this, your system is schedulable. But if you really are getting a lot of aperiodic tasks and your bandwidth is very slow, then you probably will have a queue of them. Okay. Now let's move on. So we're still talking about real-time tasks and scheduling them. at this point, we're done almost with uniprocessor scheduling. So I'm going to talk a little bit about other stuff, and then we'll come back to multiprocessor scheduling. So let's talk about synchronization in real-time systems. Now that we're done with uniprocessor scheduling, if you remember all the when I started uniprocessor scheduling, what did I say? I said we're assuming periodic tasks and independent tasks. So basically, there is no dependency between the tasks. I can run them any order I want, technically. Now, let's see what happens if your tasks are dependent. And one notion of dependency could be synchronization, right? If one task has locked a mutex that other task needs, then that other task is dependent on the one who has locked the mutex. So there is the dependency over there. Now, the problem of deciding whether or not a set of periodic tasks with dependencies is schedulable or not is NP hard. So this is something that we didn't have previously, right? Previously, we actually very freely talked about feasible schedules for any task set because you can come up with one in polynomial time, as you saw with like EDF or LLF. So that was feasible polynomial time. Now, the moment you introduce dependency between your tasks, meaning that this should run first and then this should run, and if I haven't executed this task, I cannot execute other ones, and then there is dependency for the upcoming tasks and so on and so forth. If you have those relationships and you want to just see if any schedule could work to produce a feasible schedule for your task set, that's an NP hard question. Okay. I mean, given that you want to enforce this mutual exclusion, right? Given that you want this mutual exclusion, it would be it wouldn't be feasible. It would be NP hard to solve. So there's a paper I have cited. If you're interested, definitely look it up. Now, actually, it's a thesis. So the other problem, so this is one problem with synchronization. Basically, it makes it really hard to even find a feasible schedule for our task set. The second problem with general purpose synchronization primitives that we have seen and implemented in the previous lectures is that they lead to priority inversion. So this is the first time I'm actually defining priority inversion. I actually added this line today in the morning. I went through the slide and I realized that I haven't really defined what priority inversion means. So I added this line. So basically, priority inversion means that a high priority task indirectly, this is very important, indirectly is preempted by a low priority task. So I'll show you an example. So here is an example. Let's say I have 3 priorities in my system: high, medium, and low. And this is time. So on x-axis, I have time, and on y-axis, I have the priorities. Let's say task L runs. There is no other task in my system. And let's say at this point, task L locks the mutex R1 or resource R1, whatever you want to name it. So now R1 is locked by low priority task. Let's say at this time it gets preempted because a high priority task has come. And let's assume that the high priority task wants to acquire the lock here, the same mutex that R1 has locked. Now, if the high priority one wants to to lock it, it gets blocked. So it cannot run. Now, so far, so good. It's actually not so good, but it's fine. So now this high priority task got directly preempted by this low priority task because of the synchronization. That's sort of fine. In good systems, in systems that are well designed, at this point you somehow inform this low priority task that you have to, wrap it up because there is a high priority task waiting for you. So get out. So you could send a signal to the low priority task, and if the program is well designed and well engineered, then this low priority task will relinquish the mutex and terminates. So this is not the problem that we're talking about, priority inversion. Priority inversion usually includes a medium priority task here that is going to come and mess things up. So let's say at this point, a medium priority task comes in. Now, since this is a medium priority and has a higher priority than low one, it will preempt the low priority and starts running. So what has happened? Now we have priority inversion. Why? Because this medium priority guy has a lower priority than this high priority guy, and it's kind of preempting this high priority guy because it's not allowing this low priority guy to finish so that high priority can start. It's just meddling inside and making things hard for the high priority task. So this is called priority inversion. Now we have a priority inversion. So it's not the fact that this L guy can preempt H. That's what synchronization means. It's this medium guy who has come in and caused this priority inversion. Now, at some point, this medium guy is going to be over. Then L finishes, releases the mutex, and eventually high priority can run. Now, the problem with this is, I mean, you could imagine this this being a big problem because now it's kind of like unpredictable when it comes to H, because now the execution time of H doesn't only depend on L, it also depends on when and how long M is going to take. And there could be so many M's. So even in a well-designed system that wants to, signal L to relinquish the lock, right before L does that, you could get new M's. And in that case, L never can release its lock, and then H would be blocked by these medium priority tasks all the time and could start. And so this is absolutely bad for a real-time system. You really don't want that. And here is one example that actually happened in reality. So this is about the Pathfinder, the Mars Pathfinder, which landed on Mars in 1997, and so after a while, like after a few, after it started gathering data and transmitting them, they realized that the robot keeps restarting. So it restarts, it loses all the data that it has gathered, and then it does it again, and it does it again. So like it's just restarting and not doing anything. So turned out that it was because of priority inversion. So there was this low priority task that would publish the data on a bus. But in order for it to use that bus, it would have had to acquire the mutex on that bus. There was a high priority task also in that system that used the bus, and it had to also run frequently. So whenever this low priority task was running, this high priority task would be blocked. So far, so good, no problem. But then there was another medium priority task in that system that was doing like some other stuff unrelated. So it didn't have anything to do with the bus, but it was running for a long time. Now, what happened was, okay, there was another, so far 3 components, a low priority and a high priority, both of them using a bus, and a medium priority that was running, but it was long. There was a watchdog that its job was to check that this high priority task runs at least some time every time interval. Now, because of this priority inversion, now low priority task holds the lock, high priority task is blocked, and now medium priority is running instead of low priority. So both low priority and high priority are just waiting for this medium one. So high priority wouldn't run for a long time. And this watchdog would realize that, oh, high priority hasn't run, and that's bad. So it would restart the system. And then the same scenario would happen again. And then the watchdog would restart the system. And this would happen again and again and again. And every time this happens, it's kind of like you lose everything. You're rebooting your system. So I think eventually they fixed it. I think it was a software fix that they sent to the, when they realized what it is, I think they fixed it. But so this is an interesting instance that these things could actually happen in reality. Okay, how do we fix it? One fix that you could think of is called a priority inheritance protocol. It's a simple one. So the idea is, let's say I'm a low priority and I hold the lock, and then a high priority task comes and gets blocked on the lock that I'm holding, or a mutex that I have locked. Then I should inherit that high priority's priority. So my priority would be elevated to that high priority task that I'm blocking. And in essence, this prevents the medium priority to come and preempt me, because now I'm no longer low priority, I'm high priority. I was about to use the B word, but so I'm high priority. You medium priority guy cannot preempt me, and that's good. So this prevents priority inversion. Simple, right? And so it's good, but the problem with it is that it doesn't prevent deadlock. It could cause deadlock, in fact. Here is an example. So I have, eliminated the medium priority, because in deadlock, the medium priority doesn't matter because it's not sharing the same lock with high and low. But let's say I have this situation where L has locked R1 and H has locked R2. And then at this moment, H wants to also lock R1. So it tries to do that, but it gets blocked. Now both of L and H now have high priority because the L's priority will be elevated. So now I have 2 high priority tasks. One has locked R1, one has locked R2. Now I go back to L. I run a little bit. Let's say at this point, L also wants to lock R2. Now I have a problem, right? Now I have a deadlock. So it's a cycle. You probably should remember this from 252. So I have a deadlock. The other problem with priority inheritance protocol is the problem of chained blocking. So it's different from priority inversion, but it has the same flavor. So let's look at an example. So what does chain blocking mean? Let's say I have L, it locks R1, then M comes and it locks R2. Then it tries to lock R1 but then it can't. So now the L's priority will be elevated to M because it has locked M. Now let's say H comes and H also wants, now H wants R2. Okay, look at the difference here. So, so L now wants R2, but then R2 is held by M, who is blocked by L. What happens is now M is blocking H and L is blocking M. We elevate M's priority to H's because H is blocked by M, but does that solve any problem? Not really. So the problem here is that although H does not need R1, it has to wait for this low priority guy because of chain blocking. See, the chain is L depends on M and M depends on R. So H now depends on L, which is not good, right? In reality, H did not need R1, so it shouldn't be blocked by L. So this is called chained blocking, which, as you just saw, elevating the priority of L or M does not solve this issue. And H would still have to wait for L. Okay, so these are the two problems with priority inheritance protocol. One, it doesn't prevent deadlock. Second, it does not prevent chained blocking, both of which are detrimental for any real-time. I mean, I would say for any system, but especially in real-time systems. Okay, so how do we fix this? There is another protocol that you can use. It's called priority ceiling protocol that would address both of these two issues. How does it work? So the idea is we're still going to use the elevation that we saw with priority inheritance protocol. So we're still going to do that, but we're going to take another step. It's very similar to what we did with deadlock prevention methods. If you remember, with all the methods that we use to prevent deadlock, it's kind of requires all the tasks to upfront say what resources they need. So before a high priority task runs, it should, using a protocol or an API, say that I need this mutexes or these resources. The same with medium priority, the same with low priority. So you upfront know all the resources that each one of them needs. Okay, so that's that. So assume that we know that upfront. What do? We're going to assign to each one of the resources, to each one of those mutexes, if you wish, whatever resource that they're competing. We assign to each one of them a priority ceiling. What do we assign? So this should be equal to the highest priority of any task that can lock that resource. So because I know what tasks need this resource in their execution, I will assign to each one of them the highest priority of any task that would need them. So now that's set. So now I have a ceiling for each resource. Now what do I do with that ceiling? So each task, now I start my system. I start running my system. Each task, I allow them to lock a resource if and only if their priority is more than the priority ceiling of any resource that is currently locked by other tasks. So let's decipher this line. So I hope you now know each resource has a ceiling. Now, at any moment in time, some of the resources are locked. So let's look at the set of resources that are currently locked by some task, right? So this set, I look at all the resources, and then I pick I set the ceiling of these ceilings. So I look which resource has a higher priority ceiling. So I take that number into account. Okay, so this becomes a key. Basically, I look at all the locked resources and I look at the highest ceiling there, and I memorize that number. Now, time goes by. Some task wants to lock another resource. I look at the priority of that task that wants to lock a resource. And if the priority of that task is higher than this number that I have memorized, then I allow that task to lock the resource, and then I will update what I memorized. If not, I decline that task's request. So that task becomes blocked. Okay, a little bit of, maybe a little bit confusing. If you think about it, hopefully it clicks. And again, we're still gonna do, elevate tasks priority. So this actually could happen still, that a high priority task gets blocked by a low priority task. This is possible because let's say it's the beginning of the game, the beginning of the, the running of the system. No resources are locked. So the number that I have memorized is 0 because no resources is locked. Now my low priority task comes in and locks a resource. That's fine because what I have memorized is 0. So the priority of low priority task is more than 0. So I allow that task to lock. Now that this has happened, now I have one resource that is locked. That resource has a ceiling. So I memorize that number. Now in future, if another task comes in and wants to lock another resource, I will look at that task's priority and I compare that with what I've memorized. And if it is less than that, I will decline the request. Here is an example. I think it's good. First of all, it prevents deadlock by definition, actually, because let's say I'm just bringing the old example that we had. L locks R1. Now, what happens? Now, at this point, because I know, so if you go back to the example we had, we know at this point that this example, both H and L want both of the resources. So both resources, they have ceiling of H because they are both are wanted by the high priority task. So the ceiling of R1 and R2, the ceiling is H. Now, I allow L to lock R1 because at this point no resources is locked. But now the ceiling becomes H. Now H runs. At this point, it wants to lock R2, but because its priority is not higher than high, because high is the number that I have now memorized, because high is not higher than high, then I don't allow it to lock R2. So this means that H will be blocked. I will elevate L's priority to high. Now it runs, it acquires R1 and R2. It's still possible, right? Because Yeah, this might be problematic. I think L's priority should be more than high to be able to lock R2. I have to clarify this. Okay, so each task runs at its assigned priority unless it has locked any resources needed by higher priority tasks. Oh, sorry, it's other tasks. So let's clarify right now. So when we want to, look at requests, we look at resources that are locked by other tasks. So at this point, no resources is locked by other tasks because H has not locked any resources. So L is able to lock R2. Okay, so the key was this other tasks that I forgot. So at this point, L will acquire R2, gets done, releases R1 and R2, and everything is now fine, right? Okay. So at this point, this L guy is done. So then H can run. Okay. The reason here H can lock R2 is because there is no task left in the system. So there is no resources that is locked by other tasks. So to be clear. Okay, it also, PCP will also prevent chained blocking. So the same example that we saw with priority inheritance and why it's not working, here I show you that it works and it doesn't allow L to prevent H from running. Sorry, yeah, it doesn't prevent H from running because M cannot lock. Look at the example. So L starts, it locks R1, then M starts. M wants to lock R2, but it can't because M wanted R1, right? So the ceiling of R1 is actually M, but M is not higher than ceiling of R1, which is M. So M cannot lock it. It gets blocked. Now we elevate L's priority to M. Now here comes the beauty of it. Now H comes in. H wants to lock R2. Yeah, let me go back to the example. I might have made a mistake. Yeah, so this R1, yeah, I've made a mistake. So R1 is only needed by M. So here in this example, I guess I can fix it right away. But what is going to happen? Okay, I don't want to spend some time on this. But what will happen? There's a mistake in the slide. I will fix it. So here H wants to lock R2. And it can because the ceiling of R1 is M and H is more than M. So, and that's the whole purpose of this. So H wouldn't be blocked by L. So this part of the slide is actually not correct. So this doesn't happen. This guy will run. Oops. Anyways, so I guess I can fix it later. This will run immediately, and that's the whole whole thing about it, right? Because it should run, it should be able to run, and at this point it gets done. Then we go back to this guy. Yep, now it's correct. Let me see if I can. Oops. Oh, I think it's. Okay, yeah, so this is what's going to happen. Now, let me go a little bit down. This comes here, and I delete this one. Okay, so here M got blocked because M was not more than M, right? This R1 was the resource that was locked, and its ceiling was M, and M was not more than M, so it got blocked. Now H comes. H, okay, I'm going to delete this as well. H wants to get R2, and it can. Why? Because R2 is only needed by M and H, and R1 is only needed by M and L. Sorry, M and L, yeah. So ceiling of R1, which is the only resource now that is locked, is M, and high is more than M. So it's able to lock R2. So this is, now contrast this one with the example we saw here, where H got blocked by L. Now H doesn't get blocked by L. So we have prevented chained blocking. So H now can run. Okay, so good that okay, so I probably have to change the animation as well, but I will update the slides after the lecture. Okay. Now, this problem of priority inversion actually happens with all sorts of priorities. So it's the priority is not just high-low, right? In real-time systems, as we saw, for example, with EDF, the priorities are identified by deadlines. So deadline tells, like, sets your priority, right? So you could still get priority inversion. In the case of EDF, it would be deadline interchange. So let's say you have two tasks. One has earlier deadline than the other one. Now, if the other one runs first before the higher priority one comes and locks the resource, and then the higher priority which has a earlier deadline comes, it wants to lock that resource, but it can't because it's already locked. So you get deadline inversion because it's priority inversion. So to deal with that, if you want to do something like priority inheritance, you can do deadline exchange, meaning that you could change the deadline of tasks to basically do what we did with priority inversion. The same with with the other protocol. So you can basically, again, synthetically or artificially change deadline of tasks to change their priorities if you have to. Okay, so that's the discussion with synchronization. Now here comes the last. Actually, before we go to scheduling multiprocessors, let's talk about still in the flavor of priority inversion. Let's see if multiprocessor has anything to do with that, and the answer is yes. So in a uniprocessor, right, if let's say a high priority task comes and preempts a low priority task, that's fine, right? It's acceptable. But is it also acceptable in multiprocessor setting for a high priority task to preempt a low priority task? Well, it seems to be, yeah, sure. What's the difference? But here's the difference. Here's an example. Let's say, let this example finish. So let's say I have a low priority and a high priority task on CPU 1. So let's say this low priority task locks R1 somewhere here. Then this high priority task comes and it doesn't want to lock anything. So it preempts the L and it runs. And at some point it's done. Then L runs and L unlocks R1 at some point. So this, if this was the only CPU we had in the system, this was, yeah, sure, this looks fine, right? High priority task preempting low priority task. But what happens if I'm actually running a medium priority on this CPU too? So let's say I'm running this medium priority. It's not impacted by any of this until it wants to lock R1 that was locked by L. Now, well, what happens is, well, it's locked, so it gets blocked. Now this M guy gets blocked by L, and L is blocked by H. So M cannot run while L and H are running. So M finishes here or gets to run here. Now, is this good? Well, maybe, maybe not. So it really depends, because now it's as if this H guy, this high priority task, has preempted both L and M, not just L, but also M. Now you have to ask this question in your system when you're designing it. Is this high priority more than L plus M? Or is it just more than M individually and more than L individually, but L plus M is more than H, right? This should be decided here, because right now this system assumes, this schedule assumes that H is more than L plus M, because now H has blocked both L and M. Okay. Now, the last topic that I'm going to cover with real-time systems is the topic of multiprocessors, as promised. So we're going to look at 3 categories of scheduling policies. One would allow no migration. So basically, it's a fixed pinning. So when your task comes, we pin it to a particular CPU, and it will stay there forever. So that's one category. So this is called partitioning, right? Because you partition your tasks between the CPUs and you don't allow them to migrate. Then we have the second category, which is restricted migration. With this one, you allow jobs to run on a single CPU, but different jobs from the same task could run on different CPUs. So in a sense, in the first one, each task and all its jobs are assigned to a single CPU and they cannot migrate. In the second one, in the restricted migration, we allow different jobs of the same task to run on different CPUs. Well, we don't allow those jobs to migrate. So if a job is assigned to a CPU, it will stay on that CPU until it finishes. And lastly, we look at full migration. So basically, we will put jobs on CPUs, but then we allow them to migrate, going from one CPU to another CPU. Okay, so these are three categories. Now we put these three categories next to the three categories we had before for scheduling uniprocessors, which was static, dynamic, and fully dynamic, with their definitions, right? Now we have 9 cells in this table. A static with no migration, a static with restricted migration, static with full migration, and the same with dynamic and fully dynamic. So the first element in this pair is a static, dynamic, or fully dynamic, and the second one is no migration, restricted migration, and full migration. Now let's look at these categories. So anything with no migration, so basically this column, right? Looking at this column, if we don't allow migration, what happens? Let's focus on that. So it's proven that finding an optimal assignment of periodic tasks, let's say you have n periodic tasks and m CPUs, is NP hard. So you cannot find a feasible schedule for your n periodic tasks if you don't allow migration in polynomial time. So it's a NP hard task, and you can reduce it to bin packing problem and show that it's NP hard. So it's a hard question. So that's first problem with this column. All the elements in that column, no matter what scheduling policy you choose, it's going to be impossible. I mean, it's going to be an NP hard problem to find a feasible solution. So people have thought about many heuristics. As you can actually assume, there are many heuristics for bin packing. So many of them have been used for this problem as well. These are heuristics, so they may or may not produce good solutions. Now, some of the famous ones are first fit or best fit. So you basically, with first fit, you just go through your CPUs, you find the first one that has enough capacity for this new periodic task. For example, if you're doing, EDF, you can just look at the utilization of that CPU and then assign it. If you're doing rate monotonic, you can again use the formula for schedulability to assign. So that's first fit. You could also do best fit. So pick the CPU, assign it to a CPU that has the minimal remaining space capacity. So basically, with this policy, you want to make one CPU full before moving to the next one. Now, it can be shown that no matter what you do, even the optimal assignment, let's say you have all the time to find it, you can show that there is a test. There's a set of tasks for which any scheduling policy in these classes that are specified by this notion. So any scheduling policy that does not allow migration, no matter what, there is a task set that the worst case utilization of your system is basically m+1 divided by 2. What do I mean? Let me decipher what I just said. So you have M CPUs, right? Let's think about EDF. EDF was telling us that you can utilize 100% one CPU. Now you have M CPUs, so you wish to utilize M times 100%, right? Because you have M of them, and you want all of them to be fully utilized. So you hope that the total utilization of your system is close to M, right? Like M times 100%. That's the best you can get, right? You have M CPUs, each one of them can have utilization of up to 100%. So you want to be able to run a task set that has a total utilization of M times 100%. So that's what you want. Now you can show that if you don't allow migration, then if you have a task set that has a total utilization that is more than half utilization that is possible in your system, it's basically M plus 1 divided by 2 times 100%. That's half of your capacity, right? So I can give you a task set which has a total utilization of this much, and I can show that no matter what scheduling policy you pick, you're going to miss somebody's deadline. So there is no feasible schedule for this task set. Basically, what that means is there are worst case scenarios that you're wasting half of your system if you don't allow migration. I'm not going to go to the proof. It's actually a one line. You can read it. So here I'm explaining how to construct that task set that no matter what scheduling policy you use, you cannot schedule this task set and somebody will miss their deadline. Okay, so seems like this column is not a good column if you don't allow migration. First of all, finding the best possible schedule is NP hard. Second, that best one has a worst case scenario where you cannot utilize even more than half of your system. So okay, so maybe we shouldn't. This, however, is very simple to implement, right? As you might imagine, you're not allowing any migration. You just set tasks to CPUs and you run your system. So it's easy to implement, but it's hard to find optimal, and even that optimal could be a could lead to a bad utilization. Now let's look at some other elements in that table. What about this one? DR. So this is dynamic and restricted migrations. So one example in this class is, let's say, so because it's dynamic, right, you can assign priority to jobs. And because it's restricted, you can run different jobs on different CPUs. So it's kind of like a good fit. So jobs have fixed priority, but each one of them has to run on a single CPU. So this is one example, right? You could potentially do this. Yeah, it's suitable when you have task sets in which jobs have considerable amount of a state. You don't want to migrate your jobs because your job has a lot of cache, a lot of memory, and if you migrate them, you're going to introduce a lot of unpredictability because now all the data has to become in the new place. So the migration is a headache. So you want to avoid it. So this is a good class of a scheduling policy to use in that setting. The other one that you can think of is dynamic and full migration. So one example for this class is global EDF. So basically, you have a single queue of tasks. If you remember what we talked about scheduling, the first and naive way was that you put a single ready queue, and then you schedule on all your CPUs. So if that's your system, if you employ, if you implement EDF for scheduling this single ready task, then that scheduling would be a DF schedule because it's dynamic. You're using EDF, and EDF is dynamic, and it's fully, you're allowing full migration, right? Because this EDF guy is going to put tasks, put jobs on different CPUs. Jobs can be preempted, go back to the list, and then run somewhere else. So you're allowing full migration, but it's dynamic. Now another class is SF. So a static and full migration. Now you could imagine, well, instead of using EDF, use RM. So that brings you a static, but it's still fully dynamic, it supports full migration. So one thing that you can show for all of these three, and actually for any XY based scheduler, where this X is not equal Y equal F. So any scheduling this in that table with X and Y, where X and Y are not FF, so fully dynamic and full migration, any other cell in that table, they suffer the same exact worst case utilization. So at most, they can utilize half of your system. God, what time is it? Oh, I have time. I should probably should set an alarm for the end of the class. Okay, so again, all of them will suffer the same worst case utilization. Now, what about FF? Now, one example of FF that you could do is to use LLF for your global queue. So we saw using RM, we saw using EDF. What if I use LLF for this queue? Well, it would produce an FF scheduler because now you're fully dynamic because of LLF, and you allow jobs to migrate fully. So you have F in the other elements, but you can easily show that it wouldn't produce an optimal schedule. So it's not hard to show that similar to EDF, it wouldn't produce an optimal schedule. So at this point, you're like, okay, what on earth can I do? It feels like when it comes to my multiprocessors, things are not, good looking. Because again, if you remember with uniprocessor, we could easily achieve 100% utilization by using, EDF, for example. But now what I'm saying is all the other cells that I showed you, there's a worst case scenario that you can utilize your system by half. And that's the worst case. You cannot utilize more than that. So there is a good news and there's a bad news. The good news is actually there is a scheduling policy you can use to achieve full utilization. So it works, it's a notion called P-fair scheduling, proportionate progress. The fact of the matter is that I'm not going to cover it, unfortunately. I covered it last year, so I probably will put a link from last year's lecture for those of you who are interested. I'm going to actually move on from it. But the part that I'm going to say is it actually works. So you can prove that. So the idea is basically we're going to turn it to I think the notion is going to be we're going to introduce deadline, like another kind of synthetic deadline for our tasks and jobs, and schedule based on that. So we're going to turn the problem back to a notion of EDF, and then we will achieve high like 100% utilization on all of our CPUs. But again, I'm not going to actually dive into it. So if you're interested, definitely take a look. I actually have, I mean, the slides should be enough if you want to study it. Again, I will put a link to me describing the algorithm from last year. But again, I'm not going to spend time on it. And then there is a proof that it actually can utilize your system, fully utilized. The downside, however, with PFAIR is that it's very expensive to implement. So it's kind of like again, another scheduling policy that we talked about that is not practical. It's kind of like just there to be used as a benchmark. And then whenever you come up with a new mechanism, you can compare yourself with this PFAIR. And there are actually many. So there are many versions of PFAIR, like PD, PD2, ERFAIR. So these are extensions of PF to mitigate some of the problems that PFAIR has in terms of being more implementable. Okay, so that's pretty much it with real-time systems. Now, I have a few more minutes to basically start the next lecture. Oh, actually, let's cancel this. I have to change it and then upload it on GitHub. Okay, so where are we in the course? Okay, will you address the updated grade distribution of the labs during the tutorial? What is that? Will you address the updated grade distribution of the labs during the tutorial? Oh, yes, I will. Yep, I will talk about the labs during the tutorial. Okay, so where are we? So far, we have talked about CPU mostly and how we can time share it and everything that is attached to that. Now, in the lectures that are coming, we're going to focus now on memory, and we're going to do similar things that we did. With CPU, we did time sharing. With memory, we're going to do space sharing. So the mission is still the same. We want to create an illusion to each one of our processes that you have access to your virtual memory, which is very big. I think we had that calculation that for, or maybe it's coming. I sincerely don't remember, given all the things that I'm going through, that the size of virtual memory is huge. The size of physical memory, however, is very limited. Now, this physical memory is shared by all the processes that run on our system, and each one of them thinks that they have access to their entire virtual address. So this is the job of operating system, to actually create that illusion. The physical reality, as I described, is that we have actually limited capacity, and it has to be shared between the CPUs. So that's where we have space sharing. Now, so far we talked about scheduling, which was basically multiplexing the processor. Now we're going to talk about memory management and do similar things to achieve the same goal. What are the goals of memory management? The first and the most important one is protection. So we want to protect each process from itself, from others, and we also want to protect the operating system from the other processes. So we want to protect kernel data. We want to protect programs data against each other. We want to have a special access permissions to different data. And so although we want isolation, we also want to allow some controlled overlap, right? We want programs to share data. For example, they should be able to share a library data. If you have a C library, you don't want to have multiple copies of it. You want to have one copy and then allow different processes to share it. So that's a controlled sharing. So we want isolation and also controlled sharing. So that creates some, interesting discussions that we should have. So here are some important examples of overlap, a controlled overlap. So one of them is basically shared binary files. Let's say you fork. What is happening is the forked process, until it calls exec to switch to another binary, it uses the same binary file. It's the same code, right? So as long as you haven't yet called exec to switch to another binary file, you're basically using the same piece of code. So that's one kind of sharing if possible. So you want to share code, share binary if possible. The other one I gave an example was shared libraries. The other one is, you studied this interprocess communication, right? So you want to be able to share a memory for communication between different processes. They could write and read from that shared data to communicate with each other. The other one that we'll talk about is memory mapped files. So you want to be able to map a file to memory and then allow different processes to read and write from that file. It's very similar to this inter-process communication. And again, I talked about this user system library. So all of these are examples of controlled overhead that we want to support. So the second goal, the first goal was protection. The second goal is allocation, basically implementing that space sharing, making decisions on who gets what and how much memory we give every single process. So we're going to actually talk about both of them. We start with protection and we end the lecture with allocation. Okay, so before I think this is going to be the last slide for today. This is just a background, basic stuff about addresses. So let's say if you have k bits to address memory or anything, right? With k bits, you can address 2 to k different things, right? That's combinatorial math, discrete math. So that shouldn't be a problem. Now, when we're talking about memory, each one of these things is just a byte, 1 byte of memory. So if I have a system that has k bits to address memory, that system can potentially address 2 to k times 8 bits, because each one of those things is a byte, 8 bits. So now you can actually convert stuff, right? What is 2 to k bytes? You can say 2 to 10 bytes is 1024 bytes. The other way to show it is 1 kibibyte. I think that's what they say. This I, it's different from KB. KIB is 2 to 10, and then KB is 1000. So it's a little bit more than 1000. It's 1024, and we say kibibyte. Although in the lectures, I'm going to just say kilobyte, but what I mean is kibibyte. So KIB is what I really mean. So how many bits to address each byte of a 4 kilobyte memory? So let's say my entire memory is 4 kilobyte. How many bits do I need to address them? Well, you turn it the other way. You say 4 kilobyte is 4 times 1 kilobyte, which is 4 times 2 to 10 bytes, which is 2 to 12 bytes. To address 2 to 12 bytes, you need 12 bits. How much memory can you address if you have a system that has a 20-bit bus or 32-bit bus or 64-bit bus? So here is the end result. For your systems, most of your systems now that are 64-bit, the amount of virtual memory that you can address is 2 to 4 exabyte, which is 2 to 14 petabyte, which is 2 to 24 terabyte, which is 2 to 34 gigabyte. This is humongous. So this is way larger than today's memory capacity. So for a 64-bit system, our capacity is a lot. For a 32-bit system, we can address 4 gigabyte. For a 20-bit system, we can address 1 megabyte. Okay, so that's pretty much what I have. Hopefully, I'll talk to you this afternoon about lab 4 and 5, which are going to be merged. I mean, I got rid of 5, so it's going to be just 4. Take care, be safe. Talk to you later. Bye-bye.